Okay, so, we were discussing interaction of electron with an external electromagnetic field. We started with a static magnetic field, hence the vector potential A mu CL of x is given by 0, A of x, and if I denote A mu tilde classical of q to be the Fourier transform of the vector potential, then the Fineman amplitude for the process is given by I times m is equal to I e gamma I f1 of q square plus I sigma I nu q nu divided by 2m f2 of q square with u bar of p prime I e, and you have u of p times a tilde I classical of q. This is what is the Fineman amplitude. What we will do is that we will evaluate this amplitude for a non-relativistic electron when the virtual photon is also weak, in the sense that it is a low energy virtual photon. Okay. So, we will do that. So, what we will do is that we will use the exact expression for the Dirac spinors that we have derived when we quantized the Dirac field. The exact expression is given by k slash plus m divided by 2m times e plus m u of 0. In terms of the two component spinors, this is given by e plus m divided by 2m phi of 0 sigma dot k divided by 2m e plus m phi of 0, where phi of 0 is a two component spinor. So, for spin plus half, phi of 0 is just 1 0, and it is a 0 1 for spin minus half. This is what is the notation that we had used earlier. So, we will stick with this notation, and we will work in the representation where gamma 0 is equal to identity 0 0 minus identity gamma I is 0 sigma I minus sigma I 0. And in addition, we will assume that the momenta are all small compared to the mass of the electron. So, we will plug this in this formula here. Let us first compute the first term, which involves u bar p prime gamma I u of p. So, what is this term? We will write it as u dagger of p prime gamma 0 gamma I u of p. So, u dagger p prime 0 sigma I 0 u of p. Now, we will express this quantity, we will put for u dagger p prime this expression, and also for u of p prime this, and then we will evaluate this. So, what do we get? So, when I substitute that, what I get is this implies u bar p prime gamma I u of p is equal to the Hermitian conjugate of this quantity here, which is nothing but phi dagger 0 times E prime plus m. I will denote E prime to be E of p prime. So, E prime plus m over 2m, and the second component is phi dagger 0. Sigma is Hermitian. So, sigma dot p prime divided by 2m into E prime plus m, and then 0 sigma I 0 times E plus m over 2m phi 0 sigma dot p over 2m E plus m square root phi of 0. This is what we have for this quantity. Now, I can straight away multiply this, and what I get as a result is 1 over 2m E plus m divided by E prime plus m phi dagger prime. I will use for the first one. Okay. Although the momentum dependence is out, we have to specify the spin, and then the spin for both the things need not be the same. So, just to distinguish that, I will just put a prime here. Phi dagger prime 0 sigma dot p prime sigma I phi of 0, and then square root of E prime plus m over E plus m phi dagger prime 0 sigma I sigma dot p phi of 0. So far we have not used any approximation, but now we will use the non-relativistic limit. So, in this limit E will be equal to E prime, and then this quantity will simply be 1. Okay. To order p square, it will be 1. So, to the linear order in p, this is just given by 1 over 2m phi dagger prime 0 sigma dot p prime sigma I phi of 0 plus phi dagger prime 0 sigma I sigma dot p. Okay. Now, I will use this identity here, which is sigma I sigma j is equal to delta I j plus I epsilon I j k sigma k. You see that this here you have sigma I sigma j, here also you have sigma I sigma j. So, you just use this formula and simplify that. When you do that, what you get is this quantity is simply 1 over 2m phi dagger prime of 0. Here it will be sigma j sigma I p j prime plus sigma I sigma j p I prime p I p j. Sigma dot p is sigma j p j phi of 0. Use this formula then I will simply get 1 over 2 m phi dagger prime of 0. This will give me 1 delta I j. So, this will be p prime I, this will also give me a p I. So, this p prime plus p, ith component of p prime plus p, and then I epsilon I j k. Here j I is there. So, you see epsilon j I k sigma k, and here p prime j, whereas here epsilon I j k sigma k. So, if I take it common, I will get a minus sign. So, p prime j minus p j phi of 0. So, if I just want to keep the term which is linear in q j, then this will simply be phi dagger prime 0 and minus I over 2 m epsilon I j k q j sigma k phi of 0 plus all other term. Okay. So, this is what we get when we look for the non-relativistic limit of the first term. Now, we will similarly evaluate the second term, and then we will look at the one which is linear in the momentum absorbed by the electron virtual from the virtual photon. So, what is the second term? It just involves u bar p prime sigma I nu q nu u of p. This is what we need to evaluate. So, again I will look at only terms which are linear in q j. So, that will tell me that this is u bar of p prime sigma I j q j u of p plus all other term, and sigma I j is I over 2 commutator of gamma I gamma j. In the representation that we have chosen, this is simply epsilon I j k sigma k 0 0 sigma k. Okay. So, let us consider I over 2 m times this, which is I over 2 m times this. So, this is given by I over 2 m, u bar p prime is u dagger p prime, gamma 0 sigma k is this, gamma 0 is 1, identity 0 0 minus identity sigma k 0 0 sigma k times u of p epsilon I j k q j. Right. So, this is the term which is linear in q. Again you put this for u of p, you just put this formula E plus m over 2m phi 0 sigma dot p over 2m E plus m phi 0. Since this is already linear in Q, I will set this to 0, because this, if I keep this term, it will give me a term which is cubic. So when I do that, what I will get is I over 2m phi dagger prime of 0, and this will give me E plus m E prime plus m square root over 2m, and then sigma k phi of 0 epsilon I j k minus q j. Is this right? This term I will set as 1. I will just put E and E prime to be m. Okay, so this is just 1. So what I get at the end of the day is minus I over 2m phi dagger prime of 0, this thing. Okay. So we have evaluated both the terms here. So I will plug these expressions for this as well as this here in the Fineman amplitude, and then what I find when I do that is two m times okay. This is what you are going to get when you substitute it in this expression. All right. Now, what is this quantity here? You consider b of x, okay? It is just del cross A. So, if A tilde q is the Fourier transform of A of x, then what will be the Fourier transform of b of x? It will simply be this, right? So this quantity here is just b tilde k of q. So I will substitute it here, then the Fineman amplitude is minus I 2m E times phi dagger prime of 0 minus 1 over 2m sigma k f10 plus f20 phi of 0 b tilde k of q. So this quantity if you take a potential which is minus mu dot b of x, then so you just consider the scattering of electron from this potential, use Born approximation to evaluate the amplitude. This is what you are going to get. Here mu is just E over 2m times twice f1 of 0 plus f2 of 0 phi dagger prime of 0 sigma over 2 phi of 0. This quantity is the spin operator, which I will denote as S, and hence this is of this form E over 2m times G times S, where G is the Landis G factor, which is given by twice f1 of 0 plus f2 of 0. We have already argued in the last lecture that this f1 of 0 will not receive any correction. So f1 of 0 I will just set as 1 to f2 of 0. So to leading order G equal to 2, which is what is predicted by the Dirac's theory, and f2 of 0 is something which is which quantum field theory will give us. So quantum field theory gives correction to the anomalous magnetic moment of electron, and we can compute this from the loop corrections to the vortex vector, and the loop correction to the vortex will give us correction to the anomalous magnetic moment. All right. So what we will do now is that we will compute the correction to the vortex vector at one loop. All right. So let's now consider the Fineman diagram at one loop. We will simply use the Fineman rules, and then we will see what do we get when we try to evaluate the Fineman amplitude by brute force. So what is the diagram that will contribute at one loop? The diagram which will contribute at one loop is just given by E of momentum p, some incoming electron. It emits a virtual photon of momentum, let us say p minus k. This is k. A virtual photon of momentum q is absorbed at this vertex, and finally you have k prime, which is k plus q. P prime is the momentum of the outgoing electron. Okay. So leading order term is just this, and the vortex vector for this is gamma mu. The vortex vector gamma mu, which I will set as gamma mu plus delta gamma mu at this order. So delta gamma mu I will read from this diagram. Okay. So what will be delta gamma mu for me? I can use Feynman's rule to evaluate the amplitude here, and here instead of considering the photon propagator and IE gamma mu, I will just put gamma mu here because that is what I am considering. So let us use Fineman rule. I will write u of p for the incoming electron here. Then I have a vertex here. So what will I write for the vertex? IE gamma mu. Okay, I will use the notation where gamma rho I will use. Then I have a Fermion propagator. What is the factor for Fermion propagator? It is I k slash plus m divided by k slash k square minus m square plus I epsilon. This is for this vertex here. I will write gamma mu for this. Okay. Okay, thank you. And then I have another Fermion propagator here, which I will write as I k prime slash plus m divided by k prime square minus m square plus I epsilon. Then I have a vertex here, which I will write as I gamma sigma, let us say gamma nu, and u bar p prime, and then I have this propagator here, the photon propagator, which is just given by minus I eta nu rho divided by k minus p whole square plus I epsilon. This is what I have for delta gamma. Okay. So what I will do is that I will simplify it a bit. You can see this is just given by I square I e square minus I, and then u bar p prime gamma nu k prime slash plus m gamma mu k slash plus m gamma nu u of p divided by k prime square minus m square plus I epsilon k square minus m square plus I epsilon k minus p square plus I epsilon. Okay, this is what we have. You just notice this, the numerator involves terms like this: gamma mu, gamma alpha, gamma mu, gamma beta, gamma nu, gamma nu, gamma alpha, gamma mu, gamma nu, gamma nu, gamma mu, gamma nu. It involves terms like this, and we know how to evaluate these gamma matrices. Even when you do not have trace, you just know we have done it when we consider electron scattering. So you can just use the identities for these ones we have derived earlier and plug it in here. It is a very straightforward thing. And finally, you can show that this quantity, when you use these relations for yeah. This is what it is. Thank you. So I will use those identities for these ones. Then what I get is u bar p prime delta gamma mu u of p is given by, and finally I must remember that, because you should have reminded me of this, because k is not fixed by the delta functions at all these vertices, it can be an arbitrary a quantity here, because you have k and p minus k here, k is not fixed at all. So you need to integrate over k. So d4 k over 2 pi to the power 4th. So here also it is integrated d4 k over 2 pi to the power 4th. Whenever you have a loop, you always get an integration like that. So 2I e square d4 k over 2 pi to the power 4th u bar p prime k slash gamma mu k prime slash plus m square gamma mu minus 2m k plus k prime mu u of p, this divided by k minus p square plus I epsilon k prime square minus m square plus I epsilon this is what you have. Now you have to evaluate this integration. Okay. So how do you evaluate this integration? It's a horribly complicated expression. What we will use is that we will use what is known as the Fineman parameters. We will introduce the Fineman parameters, you will see how, and then we will carry out the d4k integration by that. So you notice that if you have some quantity 1 over a b, then you can express it as integration 0 to 1 dx divided by x a plus 1 minus x b. It is very straightforward, because here you can write this, the RHS is nothing but 0 to 1 dx x into a minus b plus b square, there is a whole square here. You define this quantity here in the denominator to be t square, then you just, this integration is simply 1 over a minus b dt over t square, where the limit goes from b to a. So when you evaluate this integration, it is just 1 over a b, it is very as straightforward as this. So we will take that, and then I will introduce a variable y. This is integration over dx dy from 0 to 1 delta of x plus y minus 1. So instead of 1 minus x, I will just write it as y, and then I will introduce this delta function. So 1 over x a plus y b whole square. This is what you have when when you consider product of two terms. You can generalize this formula when you have n factors here in the denominator. So, if you have something like a1, a2 up to an, then the generalization of this formula will simply be 0 to 1 dx1 dx2 up to dxn delta of sum over xi minus 1 n minus 1 factorial divided by x1 a1 plus up to xn an whole to the power n. Okay. You can prove this formula by induction. I will not prove it for you, but what we will use is that we will use this formula to express this denominator here in terms of integration over x, y, z. So, let us do that. So, the idea here is that we will simplify this denominator, we will use this formula and simplify this denominator, and then we will simplify the numerator and then carry out the d4k integration. So, the denominator is 1 over k minus p whole square plus I epsilon 1 over k prime square minus m square plus I epsilon 1 over k square minus m square plus I epsilon. This is equal to 0 to 1 dx dy dz delta x plus y plus z minus 1 2 over dq, where d is just x times k minus p whole square plus y times k prime square minus m square plus, let me parameterize it such a way that this is z and this is x times k square minus m square plus x plus y plus z times I epsilon, right. This is very straightforward. Now, I will simplify this denominator keeping in mind that x plus y plus z is 1. So, I will whenever I write equalities now on, these are the equalities which will hold inside this integration here. Okay. So, therefore, this quantity I can write it as x k square minus m square plus y k prime square minus m square plus z k minus p whole square plus I epsilon. Okay. So, now what I will use is, I will use the fact that k prime is equal to k plus q. So, k prime square is just k plus q whole square, which is k square plus q square plus 2k dot q. Similarly, k minus p square is k square plus p square minus 2 k dot p. I will substitute these here, and what I get is x k square minus x m square plus y times k prime square is y k square plus y q square plus y 2 k dot q minus y m square, and then z k square plus z p square minus z times 2 k dot p plus I epsilon. Is that right? So just zp square if you simplify this, you can just see that you have an x k square, you have a y k square, you have a z k square. So when I add them, I will simply get k square, and then you have these two quantities, this and this, which will give me plus 2 k dot y q minus z p, and then you have y q square z p square, and then minus x minus y m square plus I epsilon, because I have again used the relation that x plus y plus z is equal to 1. Now, you see we are integrating over a variable k. Now, this comes in this form k square and a term which is linear in k. So, I can introduce a variable which I will call as L, so that this will be a complete square. So, to complete this square, I will introduce L equal to k plus y q minus z p, okay, and then this will be L square and some quantity which are independent of L, right. So, the integration variable I can change from k to L. So, let us do that. So, when you introduce L to be this, L square is k square plus twice k dot y q minus z p plus the square of this quantity, which is y square q square plus z square p square minus twice y z p dot q. So, this quantity already appears here. Therefore, my d will be, or what I can do is L square minus d is just this quantity minus the quantity that I have there. Minus k square plus 2 k dot y q minus z p plus y q square plus z p square minus x plus y m square plus I epsilon. Okay. P square is of course m square. So, this term cancels, this term cancels. Remember, they do not cancel here. So, it is just y into y minus 1 q square. Q square is not 0. Remember, z into z minus 1 p square, which is m square, and then x minus y minus 2 y z p dot q, and this will give me plus x plus y, which is 1 minus z. X plus y is 1 minus z m square minus I epsilon. Okay. So this is y minus 1, I will write again, I will use this relation minus y into x plus z q square, and here z into z minus 1 m square plus 1 minus z. So, this if I combine these two terms here, what I get? I just get this, and this will give me 1 minus z whole square m square, right, and then minus 2 y z p dot q minus I epsilon. So, let us write it as minus x y q square plus 1 minus z square m square, and then I will take this minus y z q square minus 2 y z p dot q minus I epsilon. Okay. Now, if you combine these two terms here, you just see you get y. Let us use this relation p prime equal to p plus q. Okay. So, p prime square is p square plus q square plus 2 p dot q, but p square is p prime square, which is equal to m square. So, q square plus 2 p dot q is equal to 0. I will use that relation here. Then this plus this is simply 0. So what you are left with is, at the end, if this is your L square, then L square minus d is simply minus x y q square plus 1 minus z whole square m square minus I epsilon. I will introduce something which is I will call as delta. This quantity I will denote as delta. So, if this is the notation I use, then my d is simply L square minus delta plus I epsilon, where L equal to k plus y q minus z p, and delta is equal to minus x y q square plus 1 minus z square m square. Okay, so what we did is we have simplified the denominator. Now, in the next lecture we will look at the numerator, and then we will simplify it, and then we will carry out the integration. All right.